In this video, we're going to look at graphs of the derivative function. We're going to start with the skill of being given a graph of a function, like this function here, and then from that graph, sketching the graph of the derivative function. I'll show you how to do that. The second thing we're going to look at, and the piece of information we're going to use at stationary points, you might remember these from year 11, so turning points and stationary points of inflection. The derivative is equal to 0. We're also going to use the piece of information that we know that if the graph has a positive slope, so it slopes upward, the gradient of the tangent at that anywhere along that line is positive, and so the derivative is positive. And the same for negative graphs. And finally, we're going to look at, slightly review the fact that for a function to be differentiable, so for a derivative to exist at a point, then the limit used to find the derivative has to approach the same value on the left-hand side and the right-hand side. So that if you have a cusp, so a negative gradient joining with a positive gradient, where they join, the derivative doesn't exist. Because on the left-hand side, the derivative is approaching -2, and from the right-hand side, the derivative is approaching 2. They're not the same number, and therefore the limit doesn't exist. You can use what you actually know about identifying shapes of functions to help you with derivatives. For example, our first function here is a parabola. So the equation will be something like x squared. We know if we find the derivative of x squared, our derivative is 2x. And 2x is a linear equation, and so we'll get a straight line as our derivative. Now the two equations that I've given you are simply there to help us find the relationship between the original function and its inverse. And so I'm going to get rid of the two equations because those equations don't actually fit the graph that's there. So the parabola wasn't x squared. But what we do have is that we have the derivative is equal to 0 when x is equal to -2. So on our derivative graph at -2, our derivative is equal to 0, so our y value is equal to 0. So we actually have an x-intercept on our derivative graph at x is equal to 2. Now, in terms of where the rest of the graph goes, to the left-hand side of -2 on the parabola, that gradient is negative. And so our straight line is going to be down in this negative section, down here. And to the right of -2 on our parabola, we've got positive values for our derivative, and so to the right of our derivative graph, to the right of -2 on our derivative graph, we're going to have positive values for our derivative. So it's going to be in the top half of the graph. So we can use the same idea with our next function down here, which is an inverted cubic. If you like, a negative cubic. And if we differentiate a cubic equation, we get a quadratic equation, and because our cubic equation is negative, we'll get a negative quadratic equation. So again, we look for the points where our derivative is 0. So there's 1 at that turning point there, and 1 at that turning point there. So our first turning point is at -1. And so on our derivative graph, there will be an x-intercept at -1. Our second turning point is at 1. So on our derivative graph at 1, there will be an x-intercept. And so what we need to do next is to figure out whereabouts on the graph we have positive and negative gradient. So we'll start to the very left-hand side of our graph, so over here, and to the left-hand side of -1, the line has a negative slope. So to the left-hand side of -1, our parabola, our inverted parabola, is going to be down in the negative section. Between -1 and 1, Our cubic is positive, so we're going to be up in the positive section up here for our parabola. And so our parabola is going to come up and tip over and then come back to 0. And then to the right-hand side of 1, it's negative again, and so our graph will become negative down this way. So here we have a linear function, and so the formula for a linear function is something like y is equal to mx plus c. So if you found the derivative of that with respect to x, your derivative function will just be m. It'll be equal to m, which is equal to your gradient. So on this graph, if we do rise over run for gradient, we get that the gradient is equal to 2. And the gradient is equal to 2 at all points along this line. And so for our derivative graph, our gradient is going to be equal to, if this is our line 2, it's going to be 2 here, 2 here, 2, 2, 2, 2, 2, 2, 2. For every single x value on our graph, the gradient's going to be 2. And so what we get is a straight line at y is equal to 2. And so you know that if you differentiate a linear function, you get a constant. And so what we've got here is a constant line. This one down the bottom, we've got a graph of a constant, so something like this. And so at all points along this line here, the gradient is 0. And so we know if we find the derivative of a constant, something like y is equal to c, then dy dx is 0. So the graph of our derivative function for this function here is in fact just a line along here at y is equal to 0. So I want to have a look now at moving back to our parabolas and our cubics and have a look at how we judge how steep the gradient is. So this little GeoGebra app is going to show us the derivative at the big white point on the curve. So we've got a parabola there, and at that big white point on the curve, you can see that it's got a red tangent, and GeoGebra is going to calculate the value of that tangent for us, and you can see that sitting exactly underneath that graph is a red dot. So the current gradient of that line, according to GeoGebra, is that this slope here is in fact roughly 1.5. So we're going to start it about here as our graph. And as I move the white point, you can see that it's tracking what the gradient is. And as the point moves, you can see that the slope of the line is getting less and less negative. It's less and less steep. And for each x value, it's calculating the gradient and plotting it on the xy axis at that particular point. So I'm going to come around here, and you can see that it's getting less and less negative. And then at the turning point, right there, oops, it was white, there it is, the derivative is equal to 0. And that's why our derivative graph here was quite negative over here, less negative as we come along in our x values, less negative to 0. And once we go to x values on our parabola out this way and measure the gradient, the curve is going to start to curve positively. And so I'm going to pick up that point, and move it now. And you can see that the gradient of that line is starting to become steeper and steeper. And so the derivative value is getting steeper and steeper and steeper. So in terms of what you need to show on your graphs that you draw, you don't need to calculate the gradient at each point. You just need to be able to say that for this section of the graph, it's quite negative. So for your derivative graph, you'll have something quite further down in the negative section down here. And then as the graph comes across for these x values, it becomes less negative. So wherever you start down here, become less negative, so move up. Now you know for sure that it is 0 at that turning point. So make sure that your line, wherever that turning point is, directly at that x value on your derivative graph, you've got an x-intercept. So let's have a look at some others. Okay, so for this function here, we've got an asymptote. This is a log graph. Looks like a log graph. So we've got an asymptote here, and the function doesn't exist for any of these x values. So for our derivative, we won't have any derivative here, and our derivative will also not have a value where our asymptote is. And so we're going to go to our original function, and I'm just going to pop a point and a bit of a tangent on here. And you can see that that tangent has a super duper steep positive gradient. So at roughly that x value on the derivative graph, I'm going to put a dot way up high. I don't know how high it goes, I'm just going to put it way up high. Then I'm going to move along a little bit further on the graph and look at that slope there. That's slightly less large. It's still positive but slightly less large. So at that x value, something a little bit smaller. And then I do the same thing for different spots on the graph. So at that blue point, it's slightly less. So at the blue point, slightly less. And continuing on, I'm going to do a red one up here. That's even less. And so at the red mark, even less. But it doesn't look like the graph is ever going to become 0. And so I'm not going to actually get an x-intercept over here. So it looks like for this graph, what our derivative function is going to look like is it's going to look like this. And it looks like it's going to have an asymptote along the x-axis. So let's use the same idea with this weird looking graph down here. And this might be the first time that you've actually seen a graph with an asymptotic behaviour for some values of x and then actually passing through the asymptote for other values of x. And that's perfectly fine. Okay, so let's use the idea that I used here of picking values of x to see what's going on. So let's start way over here on the left-hand side. At this point here, our gradient, that's not a very good one. It's positive, but it's tiny. And so I'm going to put a little tiny positive one there. As we move in a little bit further, slightly more positive. Closer to the x-axis at that point there, it's still slightly more positive. Still slightly more positive as we move across at x is equal to 0. Still positive, slightly more positive. And then just to the left-hand side of that, it starts to become less positive. Can you see that the slope, I'm going to zoom in here so you can see. Can you see that the slope here is steeper than that slope there? And so on our derivative graph, at the point just past the x-axis, it's going to start to come down again. And what we've got at the point 1, when x is equal to 1, at this point here, we've got a 0 derivative. So let me just mark that in, a 0 derivative there, which means we're going to have an x-intercept on our derivative graph there. And then our graph becomes, from there, more and more and more negative. And what we're actually going to find is that we have on our original graph, at x is equal to 3, we've got an asymptote, and our derivative is going to get larger and larger and larger in a negative value as it gets closer and closer to its own asymptote at x is equal to 3. So if we draw the graph of the derivative function, it kind of looks like that. Now, like I said, you're not going to get it exact. This is a bit of a rough science, okay? So what we're looking for, if we were marking this in a SAC or maybe in the exam, what they might be looking for is the actual shape of the graph, and you would be focusing on things like, for this section of the graph, it has to be positive, it needs to get a little bit bigger, and then it needs to come down. There definitely needs to be an x-intercept at 1, and then it needs to get more negative. And finally, a couple of things to watch out for. This particular function here, it looks like a cubic function, but what you've got here is you've got a point of inflection, but it's not a stationary point of inflection. There is nowhere on this graph that the derivative is equal to 0. There's no 0 gradient here. And so we'll use the idea that we used previously, where we're going to take x values and we're going to look at what is the slope at that particular point there. It's quite positive. Then move across again, slightly less positive, and across again, less positive. And I'll continue that. And hopefully you can see that somewhere between B and B, the blue one and the red one, it starts to stop becoming less positive and start to become more positive. The gradient starts to kick up again. And so what we've got for our derivative graph is a parabola, but it doesn't have any x-intercepts. Okay, last one, I want to talk about this graph here. We've got a cusp here and we've got 2 endpoints. So I said at the start of the video, for the derivative to exist, the gradient on the left-hand side has to equal to the gradient on the right-hand side. And so the gradient of this line is -1. So between x is -1, let me put it on our derivative graph, between x is -1 and 1, our gradient here is -1. And so we'll have a line that goes through at -1. Now, at the cusp, we don't have a left-hand value that's the same, and so at the cusp, what we actually have on our derivative graph is an open hole. At the end point at -1, we also don't have a limit on the left-hand side. So at that point -1, the derivative doesn't exist either. So we have 2 open holes on that. From the cusp onwards to the right, so from 1 to 3, the gradient of this line is 1. And so on our derivative graph, from 1 to 3, we're going to have a horizontal line at 1 with an open end for the cusp right over x is equal to 1 and an open end over 3 for our derivative not existing at our end point.